Hey guys. How's everybody doing? Fine.
Smells like syrup. Yeah, something in here does smell.
It does. Is anyone eating syrup? It's your, There you go. Good nose. Alright. I just found out today that our final exam date and time is posted. I don't know what the biology one is yet. I haven't heard from Dr. Saffron, but you guys have seen it. When is that?
Yeah, I thought that. One's Monday, yours was
Great.
Yeah, one's the 12th, one's
Oh, did I put the wrong date up there? It's whatever the Monday is. I have two exams. I have a CHEM107 exam and the CHEM103, and they're okay. So 12/12, is that the right date?
Yes.
Sorry, let me adjust that.
Where do you find that online?
If you go to your UDSIS,
Oh.
it gives you that. And can I get everybody together? So our exam is listed right now as 7 to 10 p.m. I always find that my students totally get burnt out by that time, especially by the end of it. So I requested to have it earlier in the day, but I don't know if anyone else has other conflicting exams during that day. So maybe what you can do to help me out with this and to argue my case is we have this room. That's not a problem. The problem is if you guys have conflicting exams. So can everyone please check their final exam schedule, see if you have any other finals on that Monday, which is the 12th. If you do, email me with the time of that exam. I would much rather have you guys in the middle of the day taking the exam, so it's more like the normal time you're thinking. I know some people work better at night, some don't. I'd rather just do it in the middle of the day. So please check your UDSIS and let me know if there's any conflicts. All right. You can talk to Ms. Terrell about finding an eye clicker. It was not during the exam. We didn't find one. But if it was during class or lab, then she might know. Any eye clicker, you guys all have your names on them, right? No. That's great. So when we find a lost eye clicker, we'll totally know who it goes to.
But it has like the ID number on the back of it.
Yeah, so how are we supposed to connect the ID number to one of 500 students in this building?
So we have to like register it online.
It's registered.
It's registered so the instructor who teaches that section can see it, but it's not. It doesn't show like that. It just shows your name for us.
By the way, I don't think I can even see any of that.
Yeah, so it is a pain, and we don't do it. We don't back out ID number to person. Put your name on it. If it gets lost in this building, it will end up in ICE 402. There's a front desk there with work study students that staff it. Go there and make sure that you have your name on your clicker, and then you'll be able to find it. If not, you might be able to find the ID code that you've registered and match it with that. And basically, we have to go click it in the class and then back out who that person was. So if that's another question on this, take it up after class. You have a question on something else? Okay. Okay, so I forgot to follow up on Chelsea's comment during last class. She said, don't let me forget, you let me forget. So has everybody agreed on what their thoughts are here on this question? What is negative pressure? You hear about it all the time. So talk to your neighbor, see if you guys agree. I don't think that you do. Throw some down.
I don't know if it makes sense. I kind of just feel like.
All right, so what do you guys think? Someone want to share their thoughts? Let's hear from Kurt.
I have no idea what the answer is.
You have no idea.
All I know is that it's probably not A and it's definitely not B.
Okay, so negative pressure can be something to do with selection and evolution. That's why I put that in there. We're talking about chemistry and ventilation, so it's not D, that's for sure. So can anyone help us focus in on which one of these answers? Where do you typically hear negative pressure? Where have you guys heard it before? Have you guys heard it before, talking about breathing? What's that?
Ventilation.
Okay, so where in ventilation?
Like when they're trying to clear a lab of toxic fumes or something like that, like the fume.
Yeah, right, so there's negative pressure in all the fume hoods. What does that mean? Does that mean that there are 0 particles of gas in there? So what does it mean? Negative compared to what? compared to the room. It means there's less density of gas particles in the hood. So which direction does air flow? Into or out of the hood? Talk to your neighbor.
Going up into the hood, so there's less pressure in the hood than air is
So, Kira, what are your thoughts?
A fume hood like sucks the fumes up and down.
Okay, so if a fume hood is designed to suck air in and out, where's the negative pressure? Is it in the hood or is it outside the hood?
It would be no, wait, hold on.
Taylor?
Wouldn't the negative be inside, and that would cause the regular pressure to move into the negative?
So we're thinking about a molecular view of gases, which I asked you guys to describe in the exam. In some places you did, some people decided not to describe the molecular view, like terminal velocity, like those kinds of things. That there's always gas particles. There are gas particles on both sides of the fume hood. But if there's a less density of them in the hood, meaning lower pressure, which direction is the gas going to flow? Towards higher pressure or towards lower pressure? There's lower pressure. It's going to go into the fume hood, which means if there's something toxic in there that you're not supposed to breathe, it's going to get sucked. The air is going to pull in and shoot up and send it outside the top of the building. So you don't want to be standing on top of the building when there's toxic fumes in here because it may just go straight up. If we know it's toxic enough, we actually treat with some sort of catalyst on the way out so it minimizes toxicity. So if you drive out 273, you guys know there's the FMC plant. Is that the name of it? There's a biopolymers plant just outside of town. If you take Ogletown Road, it's like a mile, maybe at most a mile east of town. Does anyone know what I'm talking about? There's like smokestacks and there's this stuff shooting up in the air. You guys ever leave campus?
I can see it from my apartment.
Yeah, so you can see it from your apartment. There's just gas being shot up into the air, and that's stuff that they don't want inside. Well, there's a couple different reasons, but that's one of the reasons. Is the stuff that people shouldn't breathe, so they take it out of the building and put it up into the air.
Doesn't it go right back into the air?
Well, so if you open a window, then it doesn't work, because then you just have air being circulated, and that doesn't work. So it has to be a closed system inside, and that means that the air gets pulled in from the doorways and things. It has to shoot up high enough. So there's actually places outside of a lot of chemistry buildings where you'll see a sign, no smoking allowed, air intake. So some people, you'll be in a lab in a room like this, and you'll smell smoke. But no one's smoking in here. And it's someone that's standing right where the intake vent is smoking a cigarette. All that air gets pulled in, funneled in the entire building. So you have to have different places where the air comes in and goes out, or else it's useless. Okay, so negative pressure is this idea that compared to something else, there is a lower pressure. There's a lower density of particles. So it's compared to some sort of standard. A lot of students, though, think that when we have negative pressure in our lungs, that means that we have 0 particles of air inside of our lungs. What's wrong with that statement? Your lungs would collapse because the pressure from the air outside would squeeze and you would die. And it would pull blood out of the veins, all kinds of stuff would happen. There's pressure everywhere, and that's why things kind of keep working. All right, so negative pressure is a term I want you guys to be comfortable with. So here's a big picture. Usually we just dive right into kinetics and start talking about different things. I want you to talk with the neighbor, and I want you to try to come up with a reason. Why the hell are we going to study kinetics? Which is how fast reactions occur. So talk to your neighbor, try to come up with some examples of where the rate of a chemical reaction impacts us. Why do we care about it? Alright, let's hear some ideas. Why are we studying kinetics? Give us some examples. Alex.
My thought was medications because how quickly they spread throughout the body.
Okay, great. So not only, I love it, instead of just saying medicine, you said that in order for a drug to get distributed throughout our body, the rate of distribution matters. And that's more of a physical equilibrium than a chemical equilibrium. So what chemical equilibrium would play a role there? What chemical reactions occur with drugs in our body? Do any? What ideas do you guys have? What chemical reactions occur with drugs in our body? So? Okay, so maybe it's active, and our body says, I don't want you here, I'm going to chop you up and send you out. It's happening. So these are physical equilibrium still a little bit, right? If they're not changing the chemical bonds between them, then those are going to be physical equilibrium.
Well, for like overdoses, like I think it's like Advil or Tylenol, like you can overdose on them. Like there's a specific time frame like where you actually have to be at the hospital before like, you're done for.
Totally true. So if you either accidentally take or someone intentionally takes an excessive dose, maybe you take Dayquil, and then you also take Tylenol for a headache, and then you also take some other drug, hydrocodone or something like that. All three of those have the same active ingredient, and without knowing it, you can overdose yourself because you ingested the same drug from multiple sources. So we need to know how long until we might have liver failure. So that actually is a couple of different things. So like Michelle was saying, our body fights against that and tries to get rid of the drug, but it can only do so fast. So if we know how fast the body breaks it down, we can see, well, we're at a toxic level in our blood. How long until we get below that toxic level? What else? Don?
Chemical plants, when they're figuring out how to dispose of their waste, they need to know how quickly things will break down safely.
Yeah, so maybe we can get rid of some nasty stuff into the river if it immediately breaks down once it touches water. It's really fast. Takes 100 years, you might not be willing to do that. Right? And even further than chemical plants, you think about nuclear plants. Nuclear power plants, once the rods are spent, that just means that they're not putting out as much radioactivity that they need in order to make energy efficiently, but they're still radioactive. So what do we do with them?
Put them in cool water until they cool off, and that's way too long. We bury them too.
We bury them. Because we hold it underground, if we put it in a lead container, then all that radioactivity will be trapped until either it's all used up and it doesn't react anymore, but that's thousands of years of lots of time. Or the container cracks, in which case we have leakage of nuclear or radioactivity into the surrounding, and that's what's happening in a lot of our Superfund sites, which is where we dump a lot of our radioactive material. What else? What are some other opportunities where we see that the rate of a chemical reaction really matters?
I said like bombs or like explosives.
Why?
Because like you can have like it's like stable until like you let it off and then a reaction occurs and then it could be like external force.
I love it. So, have you guys ever thought about why bombs are so dangerous? What's that?
No, why they're dangerous.
On a molecular level, why are they dangerous?
Because it collapses it forces all the pressure in your lungs and your internal organs to the back of your body, or the front, respectively.
So why? Why does it force things in a certain direction? What's a molecular description of how that ends up happening to us if we're close to a bomb? Changes the pressure where?
Around, it's in like its vicinity.
So TNT is trinitrotoluene. Trinitrotoluene is this molecule here. which starts out as one molecule of TNT. What does it break down to when it goes through an explosion? So it becomes N2O2, sometimes some NOXs, and some water, and what's one element we've forgotten about? Carbon, CO2. What state of matter do you think TNT exists in? Solid. What kind of volume does that take up compared to all these gases? We said it's about 1,000 times different, right? So for one molecule in a solid compared to in a gas, it takes up about 1,000 times more volume. And this is not one molecule to one molecule, right? This is one molecule to, I don't know, 15 or so. So if that happens very slowly, do we care? If it took 5 minutes for that to happen, it expands, we feel a little bit of pressure maybe, but it doesn't happen slowly, does it? How long does it take for TNT to explode? Milliseconds. Within milliseconds, we have that huge increase in volume. That means that that's a pressure wave that shoots out really quickly, which pushes against us, so all that air is pushing against us. And that air pushing against us is the shock wave, that's what we feel. And if someone is really mean and does the pressure cookers like in Boston and in New Jersey, then you can put the things inside of there that, as well as air moves, that those things also shoot out. That's what a lot of people have done with these bombs. So this is where time really matters. If it's slow, we don't care, but it happens so fast, so many more particles are formed, and they're all gases. So a lot of different components. What are some other ideas of kinetics, where kinetics matter? Anyone have some ideas you want to share?
You say the carbon cycle?
Okay, so why the carbon cycle? Why do we care?
Because like CO2 makes the oceans more acidic, so the rate of that we would need to know about.
Okay, so I'm going to dig a little bit deeper there. So why in the carbon cycle do we care about rates? What are the most important components of the carbon cycle? So photosynthesis does what? Takes CO2 from a gas and makes carbohydrates and water. Okay, that process, happens. It's not super fast, right? To make a tree takes 5-10 years. What about taking something that's a solid carbon source and making CO2? When do we do that? When we burn things, either trees or fossil fuels. How fast does burning things happen? Really fast, right? So the rate of these two reactions, that if one is happening much faster than the other, then we're going to shift where most of the carbon is stored, which is what we're doing. Great. Any more ideas on where CO2 is important, or where kinetics is important?
Just with the fire thing, with firefighting and how we design our equipment and our PPE and everything is very much based on how much time you have when something's starts.
We really care about time when we're dealing with trying to combat fires, forest fires as well as house fires as well as other things. Okay, so how fast the chemical reaction occurs has a huge influence on us. And the one that we're actually going to be studying the most this semester is metabolism of drugs, and exactly what you said with overdoses. So at the end of this unit on kinetics, which is a 3-week unit, you guys are going to be responsible for designing a label for a drug that suggests how frequently that drug should be taken based on what happens in the body with that drug. Okay, so to let you know, that's where we're going, and we're going to be working on that for the next 3 weeks. So to start off, just for today, we're going to be talking about kinetics a bit on the higher level. So we want to be able to describe how fast a reaction occurs, and we're going to be talking about that as far as an average rate of reaction and an instantaneous rate of reaction. You guys have done some of this already when you've looked at your workshop for the last 2 weeks. So hopefully this is not all new. But in order to talk about the rate of reaction, there's 3 different ways. We're going to say, well, how fast are the reactants consumed? Or how fast are we making products, right? It's a balanced equation. And then this last one, what is the rate of the reaction? And that's one that's going to be a common denominator for both. So in order to do this, we always have to keep in mind, like I was saying up here, wherever you start with an atom, you end with that atom. Conservation of mass. So this is all going to relate back to stoichiometric coefficients that you have in a balanced reaction. And we're going to end up asking you guys to predict how the rate of a reaction depends on how much is there. Sometimes it does matter, sometimes it doesn't. So what is the rule of thumb you guys have heard? about consuming alcohol? 1 drink per hour. What does that mean? Why do we have that?
The rate that if you drink 1 drink in an hour, it'll be below 0.08, right? That's for like the blood alcohol.
Yeah, so the general rule that we've been told is that if you consume 1 alcoholic beverage, it takes our body about an hour to try to clear that out of our system. What's that?
I thought it was 4 hours.
So the rule of thumb we're told is 1 hour. But that applies to what kind of a drink? Standard drink, which is 1 glass of wine, 1 shot, or... So that last one, so those are all a bit kind of, what's a glass of wine? It's like 6 or 7 ounces. It's not anything like you actually get poured when you're having a glass of wine. What about a beer? What kind of beer is it? It's a light beer. It's not a regular beer. It's not an IPA. It's none of those. So be really careful when you use that rule of thumb because it'll get you in a lot of trouble. So if we do that, though, why do we say per hour? So some chemical reactions absolutely depend on how much we have there to start with. Does the amount of alcohol that our body metabolizes depend on how much is there? Look at this graph and talk to your neighbor. Does the rate of metabolism, figure out how in this graph you see the rate of metabolism, and think about if that depends on how much was originally consumed.
The way he's saying it, wouldn't it be the same thing as processing so much?
How your body metabolizes based on how much you drink. Is that right? Is that what you're asking?
I didn't hear you.
The question is basically, does the amount that you're drinking have any effect on how you metabolize? Is that
Yes,
that's the question?
on the rate of metabolism, the rate of getting rid of it.
Because the rate of
All right, so Brian, what are your thoughts? How do we look at this and figure out a rate that our body clears out alcohol? Brian? How do we look at this graph and determine the rate? What part of this graph helps us determine the rate that our body clears out alcohol?
What helps us determine?
Yeah, how do we use this graph to talk about the rate of eliminating alcohol from our blood?
What do you say? So, the rate.
You want to pass for now? Javante?
How long it takes for your blood alcohol concentration to drop.
Okay, so time is a really important factor, but that's not necessarily all of it to talk about rate. So how do we talk about rate? What are the units of rate typically? What's that? It's not length. That's a rate. That's a speed of a car driving or something like that. But that's not.
Meters per second, so whatever you would call meters.
So I'm going to simplify and say change in x over time. What is our x in this case? Is it distance? It's the change in the concentration over time. Right? So it's how much the concentration changes given a certain amount of time. Where do we find that on this graph? What's that, Cosmo?
y-axis.
So the y-axis is the concentration, but it's not the ratio of concentration to time change.
That would just be like kind of like the slope, because it goes from like 0 to 5 in 2 drinks, so it'd be 2.5 as the rate.
So if we looked at the slope of this graph, that gives us an idea about the rate of this reaction. Does that rate change drastically from when you first started drinking to after you waited for a number of hours? You guys think that was a huge difference? Let me maybe redo this line. What are you confused by? Okay, so So let's clarify what the graph is. You are looking at a patient's blood that was sampled every 5 minutes or so? And those red dots are every hour of sampling. There's 5 dots in every hour, so that person was sampled 5 times. And then how much alcohol was in their blood is what is the height of the data point. So at time equals 0, before they drank, they had a blood alcohol level, blood ethanol concentration of 0. The peak that they reached, how long did it take for their blood to max out? It took an hour until they reached maximum blood concentration. And then what can we say about the rate of elimination of that ethanol from their blood? Did it vary a lot over the period of time? It took about from 1 to 4 hours, so it took about 3 hours for most of that ethanol to clear out. And was that rate pretty constant, or did it change a lot during that time? It's pretty constant. So that's where this saying 1 drink per hour comes from. But even from this data here, we can see that we spike pretty high. Granted, this is blood ethanol concentration, and blood alcohol content is a different scale. But this gives you an idea that even if we do drink 2 drinks, that it takes quite a while for all that ethanol to get out of our blood. So what we're going to be talking about is there's some reactions where regardless of how much you start with, that slope of the graph doesn't change. It's what we call a zero-order reaction. Then there's some where the less concentration we have, the slower the reaction is. And there's some there's an exponential relationship between those two. So we're going to be dealing with those different kinds. There's one more point I was going to make on this. Forgot. Oh, so is it true that no matter how much you drink, your body will always metabolize the same rate? Why are you shaking your head, Val?
Well, it depends. It can fluctuate with different things, like hormones, how much age, how much water you're retaining at the time.
Yeah. And if we oversaturate our enzymes, so this is assuming that our enzymes are capable of doing what we think they're going to do in our liver. If we oversaturate them, if we shut them down for different reasons, there's a lot of things that can happen if you're on the too much end of the scale. But on our general rule of thumb, our body has the same rate of getting rid of alcohol until it's an extreme. That's basically what we get into here. I think my computer's playing music. Let me kill that. Yeah, Beth? So we can build up, that's a good question. So our body can become less sensitive to the drug, which is what tolerance is. But that doesn't mean that our blood alcohol content is going down quicker. It means we don't feel like we're getting as drunk, and we need more in order to get that feeling, that euphoria that we get from certain drugs. And that's true of any drug, not just alcohol. So then, based on what we just saw, if we consume coffee to sober up to drive, is that a good idea? No, because that rate doesn't change. It just may make us wired as well as drunk. Question, Taylor?
I was going to say that I heard that the more alcohol you drink, the more ribosomes you get, which make you detoxify like your body faster. So that's why alcoholics usually can drink more. I don't know how really true that is.
What's that in?
I heard that people who drink too much they get more ribosomes, and ribosomes can detoxify alcohol. This is why they have like a higher tolerance because they have more things that detoxify their body.
Yeah.
They're still going to have a very high BAC, but as Dr. Wheeler just said, they're not going to be able to feel it as much.
So that's one type of chemical reaction where we care about the rate, how long until all that stuff is gone. Another major one, you guys remember hearing about this? Where is this? It's in Japan, Fukushima. So there was a tsunami that crashed into Fukushima. They have a nuclear power plant that was severely ruptured by this, which leaked out radioactivity into the water. Because tsunamis don't really happen much at all. There was an earthquake in the middle of the ocean, and that's what.
I thought Japan got hit with a lot of earthquakes and tsunamis.
This was an insane, over-the-top one. It was complete. There was, if you look at the number of earthquakes they had in a 4-day period, it was like 300 earthquakes. And out of those, like 20 of them were over a magnitude 7. It was ridiculous.
So is that what causes it? I was gonna ask you, like, what causes something? Is it just like a bunch of earthquakes happening and then like?
Yeah, so there was a fault that started sliding against it. And the worst part was, I think that they had like a magnitude like 7 earthquake. And then there's all these aftershocks that were about the same. And then they had the big one. It was nasty. So we worry about, well, what about all this radioactivity that's leaking out into the ocean? And so radioactivity, we can actually calculate how long until there's no more effect that we can detect from all that radioactivity. Does this look like an alcohol metabolism graph? Does the amount there change the rate? So the rate, which is, we said the slope of the line, is it the same here as it is here, as it is here, as it is here? So this is what we call a first order decay. This is when a reaction, the initial concentration has a huge impact on the change in concentration, the rate of the change in concentration. And then some of the stuff I used to work on before I went to graduate school is imaging. And so we can actually look inside of animals. We can inject radioactive materials, or in this case, fluorescent materials, into an animal. If they're designed right, they'll be really attracted to a tumor within an animal. They'll get specifically taken up there, and then the rest of the body gets rid of them. So metabolism happens at the same rate everywhere, but we have a higher concentration in one rate. Then we can put it inside of a scanner, and we can look. Basically, we can see inside of that animal where a lot of this radioactive material or fluorescent material was. And so this type of decay is even more extreme than radioactive decay. See how sharp that decrease is? That's an exponential decay, so that's a second order decay process. So we're going to be able to look at a graph like this, and we should be able to predict, well, how long until we have a certain amount of it left? But in order to get there, we need to do some calculations first to figure out how we can talk about these things and make predictions. So we're going to be writing 2 types of equations. One is called a differentiated rate law, and the other is an integrated rate law. You guys want to do some calculus? Okay, let's not do the calculus, but we'll use the results of calculus for integrated rate laws. That idea of time, we need an integrated rate law to talk about how concentration changes with time. But we're not going to get there yet. We're going to do some without talking so much about time. So what I want you guys to do on your graph here is I want you to draw in what this graph should look like based on the changes in concentration. And if anyone's colorblind, maybe they can ask the people next to them what the numbers look like. Are red versus black okay?
Yeah.
Not really? Okay, so talk to the people around you. Make sure you get an idea what's happening in the changes. And I want you guys to plot 2 lines on this graph. One is the number of black particles, the other is the number of red particles. So one of them starts out as 100% or 40 particles, the other one starts out as 0. What happens to those over time? Draw time points at each one of those time intervals, 10-second intervals.
Yeah, I think the last source is for A.
All right, a couple more seconds.
Am I wrong?
Yes.
Why?
So, Jose, for every black particle that goes away, every A that goes away, how many B are formed?
I only did the first.
So don't worry about the graph for now. For every A that goes away, how many B are formed?
10 maybe? I mean, there was 10 red.
Okay, can someone get some more insight, Sarah?
For every one black one that goes away, one red one.
How do you know that?
I counted.
Okay, because you counted, that's a lot more effort than you needed to do, Javante.
Because the ratio is 1 to 1, because it's A to B.
So if we look at the balanced chemical reaction above, every A that goes away forms a B. How would you adjust your graph because of that? Doesn't have to be linear. But as we decrease 10A, how many B are going to form? 10. So in the same time that 10A went away, the rate of going away of A is the same as the rate of forming of B. So we're going to be really paying a lot of attention to balanced chemical reactions to see what we expect for the rate of these two. So why is the slope of these lines, why is it really important that the slope of these two lines is the same but opposite directions? Brooke?
To show like if there's an increase or decrease, it's like staying consistent.
So that these are proportional to the stoichiometric ratio between these. Cosmin?
I was gonna say, that would help us figure out like if there was a limiting reagent and all that other stuff too.
If there was a what?
A limiting reagent, right? I know there's some limiting one, but.
So where they end up is going to tell us if there's a limiting reagent or not, but not necessarily the rate of consumption of them. Okay? So then a lot of people, I saw drawing, maybe I can draw what you guys had. If I redraw this, I saw a lot of people drawing this and this. Why is that not accurate? What are we missing? What's the most obvious thing that we're doing differently here? What's that?
You don't have the points, so I don't know if that's.
Okay, so the points aren't there, but Sarah, you had something like this. Why is this not as accurate?
Oh, I did. Because it's not like equal with each other.
What's not equal?
The red dot's exponentially increasing and the black dot's exponentially decreasing. So it's not like a 1-to-1.
Okay, so I'm going to add to what you said. I'm going to say that the rate of change of both is not based off the other through the stoichiometric ratio. So if we look at how they actually go, at any point we look at here, if there's a 1-to-1 stoichiometric ratio, we're always going to see that the slopes of them are going to be in the opposite direction. One's increasing, one's decreasing, but they're going to be the same slope, absolute value. And then over time, we notice that there's less and less change between these different graphs. All right? So this really gets us back to thinking about the stoichiometric ratio. The conservation of matter means that if A is consumed and B is formed, those rates have to tell us about that. So what we're going to be focused on for the next 3 weeks is really a graph like we just saw. So here's another reaction. We have A and B. And we have a phase of the reaction where those reactants are going away and products are forming. And then we reach a state at which we don't see any change in concentration. Does that mean the reaction stops? Why not, Alex?
It's at equilibrium, so this would be the same.
I love having you guys do workshop before class. Is that from workshop?
Yeah.
Okay, so in equilibrium, you looked at the table of data, right? And that at a certain time point, we didn't see any change in the overall concentration, but there's still reactants becoming products, products becoming reactants. That's the equilibrium phase. So the left side of this graph is the kinetic phase, where things are changing. Overall concentrations are changing. And then the right side is the equilibrium phase. So those two phases are going to take up a majority of the rest of our semester. 3 weeks are going to be spent in the kinetic phase, and then we're going to be looking at the equilibrium phase. And we're going to say, well, how do we make predictions about what concentrations we end up at based off of what we know about the reaction? So on the left side, we're concerned with how fast the reactions go and what the mechanism is. And on the right side, we're going to be talking about equilibrium constants, KEQ. Have you guys talked about whether a reaction is at equilibrium or not in your bio classes? Gibbs free energy? Vaguely familiar. Okay. What's that? Last semester, hopefully you did. So in any system that is not at equilibrium, it means that we can use that reaction to drive another reaction forward. It means that there's Gibbs free energy is not equal to 0, our definition of Gibbs free energy is equal to 0 means when we're at equilibrium, that reaction can no longer do any work. So the examples that we're going to be working on in this class for the next little bit, some have to do with drug metabolism and some have to do with air pollution. Our book focuses pretty heavy on air pollution in chapter 14. You guys know what city this is? Anyone been here? Close. Salt Lake City. So if you're driving up to Park City, no. Salt Lake City. And then is it Park City? What's the ski resort that's just outside of town? It's Park City, right? I can't remember. Right now on the spot, I can't remember. I was there last winter. And it was crazy. Flying in, you come in and you see the mountaintops, and then you just see haze. Tons of haze below it. And on clear days, I guess when there's a lot of wind blowing, that haze blows out. But it's pretty nasty thinking about what happens in the long. So we're going to be talking about where that haze comes from. What's the major source of that haze that we have, and why does it stay in the valley? Talk to your neighbor. Try to figure out your best thought on why that haze stays in Salt Lake City. So where it comes from. So question number 1, where does all that smog come from? Dan?
Cars. I don't know where it's coming from.
Why cars? Like they just look bad and so there's smog? Be a little bit more specific.
Is it like the exhaust coming from cars, like the CO2?
Okay, so there's combustion engines. So it's not CO2, but when cars burn fuel, they also pull in nitrogen gas from the air. And there's sulfur in the gasoline itself. And those generate what we call SOxes and NOxes.
But why are cars doing that over there? It looks like that, but that's not happening here. Is there a higher concentration of people driving?
So we'll get into the second part of why it stays there. So have you guys heard of SOxes and NOxes? So noxious gases, NOx. It means NO2, NO3, NO, SO, SO2, SO3. That SOxes and NOxes are byproducts from combustion. Is that when we have sulfur plus oxygen gas in a combustion engine, we end up with these. If we have nitrogen in a combustion engine, this is a byproduct, a second reaction that occurs, and it ends up forming these gases. And that's what we end up seeing. So then the second question is, well, why does it stay in Salt Lake City? Is it just like me, it really likes the mountains, so it doesn't want to leave? I have to leave, but why does it stay there? Val?
Do the mountains trap it in?
Why would mountains trap it in?
Because maybe that's something to do with the density and it can't float up over them.
Sarah, you want to add to that?
I was really going to say what she said.
That's what she said? Is that what you're going to say? Salt Lake City's a valley. And if you look down the valley, there's a big flat part in the middle, and then there's mountains on both sides. And at the ends of the valley, here and further back that way, there's also mountains. So it's like a bowl. Mexico City has a really big issue with this as well. That whenever pollution is created in there, that it stays in there until there's a big gust of wind that kind of comes and mixes it all up. Caleb?
So, isn't this happening in San Francisco too?
Not as much in San Francisco because it has the opening for the bay. But there's, maybe to some extent it does, but for shorter periods of time, and there is an opening built in where the Golden Gate Bay is.
So there's nowhere for that polluted gas to move?
That it doesn't circulate as freely this way on really still days, and the mountains kind of block the wind. But when the wind does come through, then it clears out and it looks like the right side. So what we're going to be talking about is the chemical reactions that proceed and how fast they proceed in order to make some of those gases. You have a question?
No, it's like about the fogs. We're not saying how about
Oh, so the fog, yeah, that's a whole other thing. But that's not pollution from gas. Is it just cars, by the way? You know what blew my mind? Has anyone flown into Salt Lake City? Anyone been on a plane flying in? the first thing that I saw, what's the first thing you saw flying in? Did you notice this too?
I remember seeing just tons and tons of farms and fields coming flying in.
I saw a lot of farms, and I saw smokestacks. I saw these big things spewing out all this gas, and some of those are power plants. And they're just burning fossil fuels, they're burning coal, they're burning other things in order to produce power. So it just blows my mind that they know that they have this problem, and it's still like they haven't figured out other ways to get energy in there. So that's a whole other story. So we're going to be talking about a number of different gases that are in the atmosphere, and how over the period of one day, if we look at starting in the morning, all the way until late afternoon, we have volatile organic compounds. So why is it that NO, NO2, and O3, why are these different at different times of the day? Talk to your neighbor and try to figure out why those concentrations, this is in a typical city, why do those concentrations change throughout a day? Talk to your neighbor, try to figure out a reason why those concentrations change throughout the day. What do you think, Deanna? What might contribute some of these, and when would that happen?
Like how, like a temperature?
Okay, so it could be just temperature.
If it's fermenting sauce, like different times of the day, like say car engines are used on during
During what time?
like during the daytime.
Specifically when? Why? So Brooke, what are your thoughts on where these come from? You sure?
You said that the levels would possibly change based on when the most amount of like exhaust is being let out from engines. So like in the morning, going to work and coming home from work, there's gonna be more levels like being let out.
Okay, so we only see until 4 p.m. So what gases, looking at this data, what gases can we make an educated guess are coming from car engines? Sabrina, what do you think? What gases would specifically come from car engines based on this data?
I would say both, just because it's going up at the time, like, when people are up, it's really
So this is not college students, this is regular people in the working world. So what time do most people get in their cars and drive?
I guess 4 a.m.
Not that extreme. Sarah?
I know NO2,
Okay, why?
because that kind of peaks at the hours that people are usually driving to work.
So rush hours are usually around 6 to 8 a.m. So we see a peak of which one there?
And
So where does NO2 maybe come from?
like the aftermath of
What's that?
Mixing with the oxygen that's already in the air.
So maybe NO reacts to form NO2. And then NO2 might react to form what? O3. So there might be a series of reactions that happen here, gathering from this data. Devontae?
Would it also depend on like the temperature, because it's like different times in the day, so it's like cooler in the morning, so you would have like faster reactions and more reaction like in the afternoon time, I guess.
So there might be something to do with that. So maybe if the sun plays a role in some of those chemical bonds and it breaks them and pushes them in certain directions, then that's absolutely possible. Okay? So this is what I want you guys thinking about, is where do these come from, and the peak time might give us some information about that. So let's look at the first reaction. When we have nitrogen gas, why do we have nitrogen gas in combustion engines? Why would we put nitrogen gas in combustion engines?
So it diffuses out
So what diffuses out?
the nitrogen, because if like the concentration is like higher in the air, then it's gonna go out fast.
So let's hear some additional ideas. Claudia, why do we have N2 in gas engines, in combustion engines?
I really don't know.
Shane, where does this come from in a combustion engine? Why do we have N2 in a combustion engine? Talk to your neighbors. Why the hell do we put N2 into our combustion engines to make these bad products? So Mia, what are your thoughts? Why do we put N2 into a gas engine, combustion engine?
Well, we're kind of guessing, maybe it has something to do with like the molecular weight. It's like lighter, or maybe it burns quicker.
So does our car pull N2 specifically put into our engine? Does anyone know what a combustion engine does and how it works? Okay, so Don, what happens to, how does N2 get into our engine, Don?
So it takes the gas through the line and puts it into the catalytic converter, which smushes it down and increases the pressure, and it creates a spark, which
You're missing one major component. So we need oxygen to burn, right? Our definition of a combustion reaction is O2 plus fuel gives energy, CO2 and water. All right, how do we get O2? How do we feed O2 into our car? Jose?
It's in there.
Air. Okay, what's in air? How much of the air is nitrogen? About 78, 79% of all of the air that we push in is nitrogen. How much is oxygen? About 21%, and then we have some other things. Okay? We want this, we end up with N2. And you put it into a combustion engine where it's super hot. And even though those aren't very reactive, because nitrogen is a triple bond, right? It's super stable unless we put it at really high temperatures inside our combustion engine. And then we can get these reactions that form the nodules.
I just have a quick question.
Yeah.
If air is mostly nitrogen, why do people say we breathe oxygen? Is that because that's what we?
Because they ignore the rest of it. Nitrogen's inert. Our body doesn't use it. Our body doesn't pull that nitrogen and do anything with it. So when we breathe air, it's a good point. We're breathing mostly nitrogen. So when you go diving, they actually have a lot more nitrogen in the tank. Sometimes they replace it with helium, something else is inert. So there's different things to do, but really we're only breathing air for the oxygen and to push the CO2 out. Okay, so here's a reaction. N2 plus O2, byproduct. We're not trying to do that, right? We're trying to react O2 plus fuel, but it happens to pull in N2 at the same time. So we have a reaction.
doesn't the nitrogen make it the reaction go faster? Because when people race their cars, don't they use
They use nitrous oxide, which is highly combustible and breaks down. So how do we describe how fast this reaction is occurring? What's a way that we describe how fast the reaction occurs? Miata? What's that? Okay, that's the term for it. How do we determine the reaction rate? How do we get that from information like this?
Look at the, like, maybe the stoichiometry of the, call it the reaction. I'm not sure about that.
Okay, so stoichiometry is going to play a role in something that we do at some point. Salma?
If you graph it and like look at how the slopes are,
The slope of what graph? Of what? So what axes would we have on that graph?
so the y, or the x and then the y
So the speed or the rate of a reaction is always going to be defined as the change in concentration over change in time. Just like if we're talking about the rate of a car, we're talking about the rate of change of distance over the change in time. So now we're specifically talking about the changing in concentration. So we can look at these and we can plot the changes. We can look at the concentration over time and look at the changes. And we can say, well, what's the change in each one of these? And we can pick a couple points and we can say, well, I know where it started, I know where it ended, and I can find the change. So once N2 and O2 have reacted to form NO, so that last reaction, this was the product. And now when that NO is out in the air and it's circulating outside, it comes in contact with O2 gases, and it makes NO2. So that's why we saw a first peak of NO from the cars producing it, and then at a later time we saw the NO2 gases had a higher concentration later in the day. So let's take a look at this graph. Which one of these lines represents formation of NO2 in the equation? The balance equation is here in case that helps you. So this is a graph of the data that was on that last figure.
The question was which one is NO2, right?
It's on the slide.
Get it together balance. Isn't nitrous oxide what you breathe in, like, if you're getting like oral surgery?
Yeah.
So isn't that free or not? Like, in that dose?
So
So it's
I'm not
like,
aware of it. I'm not a medical doctor, so I couldn't tell you, but not that I'm aware of.
yeah.
All right, everyone clicked in? Brianna, which one of these would represent the formation of NO2 and why?
C.
Why?
Because if you look at the balanced reaction, NO2 is the product, so you would be starting with none of it and then moving towards
So
like,
careful.
greater value.
We don't always start with none of our products. In this case, the focus I would want you to have is that it's increasing in concentration over time. Is that fair? Because we can't start with something and add more of it. So everyone in class, I think, agreed with you. The more tricky question, then, is which one of these represents the consumption of O2? Of which? Okay, make sure you read the wording on the slide because I guess I typed it wrong on the handout worksheet. So just answer the question that's on the slide on the screen. Why?
It's happening, if you look at the coefficients, it's happening at half the rate of these two. O2 and NO2
So where's the rate?
inversely the same. And then A would be half of O2.
So show me where the rate is on this to justify for a second. All right, a couple more seconds. Okay, you guys are not completely in agreement. Mommy, which one of these represents the consumption of O2 and why?
Okay, well, we said B because, oh wait, I lied. We said A, because we were basically looking at the other ratio. So we need 2 NOs, with every 1 NO, so we have, yeah,
Okay, so the way that I try to teach our class in the spring to talk about a balanced equation, how would we read that? So you're almost there, Mommy. So for every 2 NOs, can you complete the sentence?
for every 2 NOs, we need 1 oxygen to create 2
And then we're just going to add a factor of time to that. So during the time in which 2 NO are consumed, only 1 O2 is consumed to produce 2 NO2. So if we state it like that, which one is going to have a steeper slope or a higher rate of consumption? NO or O2? The one that goes away faster is the one that requires 2 in the same amount of time as 1 oxygen. So then which is the line of consumption of NO? Sarah? The green one, B, right? So the one that's going, and at any point in time, if we look, what should be the relative slope of the green line compared to the orange line? Sarah? What's that?
It would be inversely related, like the same.
The same magnitude, but the opposite sign. One's being formed and one's being consumed. Great. Okay, so if we're talking about the initial rate of this particular reaction, which of these time frames do you think would be the best to use to describe that? All right, a couple more seconds. Dana, which one of these did you choose and why? Can I get everyone back together? Alex? Dana?
I wasn't really sure, but I knew it wasn't A, so it's like too short of a time.
Why is that too short of a time? It-
Nothing really like happened between. That's like the reaction just started. I'm not really sure.
So I think your uncertainty was mirrored by most people in the class. Would anyone like to offer a strong opinion for one of these answers that they were very confident about? Brianna?
I said C because if you start at 1175, so like in between 0 and 2000, you can see roughly where the starting rates of everything is, and if you follow through to 4700, you can kind of get to see the production of NO2 cross the consumption of NO, and you can see it start to approach the consumption of O2. So you see products.
Is the rate of consumption of NO ever going to be the same as the rate of consumption of O2? It's always going to be a 2-to-1 stoichiometric ratio. Javante?
I said B because it covers like the widest and like it covers most of the points of the graph, and I didn't see that the reaction reached equilibrium yet, so I thought that it was important to put off the point.
Taylor?
I said A because if you look at the time, at 0 seconds, NO2 has 0, and then at 285 seconds, it has 0.0010. So I just thought that would be the initial rate of it being produced.
Initial rate of reaction. Does the rate of this reaction change at different concentrations? Absolutely. So if we're starting with an initial quantity, I want to be as accurate as possible. I want to try to describe what's the change in concentration over the shortest possible change in time. The closest to the time point we're interested in. And so on this graph, that includes the first 2 data points that we can use. That's A. Is there an even more accurate way to talk about the rate of this reaction? The initial rate of the reaction. What would be an even better way?
Maybe something that has like, instead of 285 seconds, maybe like 20 seconds.
Maybe if we could have less time. Maybe we could even have a tangent to the line. Oh, getting into some slopes, right? If we could know the instantaneous rate of change, the tangent to the line, at time equals 0, that would be the absolute best. That would tell us the rate of the reaction at that exact concentration. So we're always trying, so this is a kind of crappy way of determining the rate of reaction, is by taking an average, because we know it changes over time. We know it changes based on concentration for this particular graph. So if we could, we would really, really, really want to zoom in. So let's talk about using this data, because we don't have a tangent yet. We're not there. So let's calculate that. So during this first 285 seconds, that's the change in concentration over the change in time, right? That's what we defined as our rate. We go from 0.0100 molar, or 10 millimolar, down to 9.5 millimolar during a time frame of 285 seconds. we crunch those numbers, then that is a decrease in concentration of 1.8 micromolar per second. That's the average rate of change over the first two data points, the most accurate we could be with the data that you guys were given. So then based off of that, what is the initial rate of consumption of NO? Do I? Oh, the negative signs?
No, the placement's different.
Oh, the order's different?
Yeah.
So click in the answer that's on the screen. I think the order is different on your handout, your worksheet. Which one are you thinking, Pat?
I think C.
Why?
Just double because of the stoichiometric ratio.
Okay, so it's going to be... So try to figure it out. Talk amongst yourselves.
I'm ready to answer the question.
You on top of your game? Good. Quick question. What's up?
Okay, so like on the pre class, I did all the other ones and I got them right, but when I used the points from the tangent line or something, I couldn't get the answer. Like I don't know what else. I don't know.
So let's check that out right after class if you want to bring that up. But you should be able to. All right. Everyone clicked in? So Pat, can you describe what you chose and why? Why would it be 2 times the change in concentration or change in time? 2 NO are consumed during the same time as every 1 O2 is consumed. So we really need to relate that back to the stoichiometric ratio like you did, and that's awesome. So then what would we say is the initial rate of production of NO2? And why, make sure you convince your group mates that you can describe why we know this based on just the information that we have here, even if we didn't look at the table. Couple more seconds. Hannah, which one did you choose and why? Talk down.
It's like the same thing, but it's not negative because you're not using enough for the
Okay, so can you expand on that? It's the same thing, but different sign, so why?
same as the consumption.
What's the same?
The rate.
Great, the rate. I really want you to be able to say rate. So the rate that NO is being consumed is the exact same as the rate that NO2. Every 2 NO that are being used up, 2 NO2s are being formed. So that means that the stoichiometric ratio is the same, which means the rate of consumption is going to be equal to the rate of production. So why did you choose a different sign, though?
Because they're not getting used up.
Okay, so it's not going down. We're increasing the concentration, so we chose the positive. Fantastic. So then what is the rate of this reaction? Talk to your neighbor if you're not quite clear on how to answer this. What is the initial rate of the reaction? Notice I didn't specify any reaction or product.
Wait, what?
Couple more seconds. All right, close now. We don't really know. Pauline, can you share your thoughts with us?
I said that it was A, because I'm not sure, because I think that the initial rate of is like it's the steepest, if we're looking at the initial there, then that would be.
Okay. Someone else want to try to add to that? Morgan?
I
And why?
I picked C because I remember I got this wrong on the 7th homework, so then I saw that the rate of reaction is equal to the reaction or production rate of the element in the equation with the lowest coefficient.
No. Close. For this one, it happens to be what you defined as. But the rate of the reaction is defined as, what would the rate be of consumption of something if we had a stoichiometric coefficient of 1? If. Do we have one in this case? We do have one in this case. So the rate of consumption of O2 is the rate of reaction this time. But sometimes it's not. If we have stoichiometric coefficients of 2 and 3, then neither of those are the rate of reaction. It would be extrapolating down to what if we had a stoichiometric coefficient of 1. It's basically saying that if we know the rate of reaction, we can multiply that by a stoichiometric coefficient and find the rate of any of the consumption or production. We'll do some more examples with that. So then which one of these is the rate of consumption of O2? Taylor? It would be B. Okay, so if you have a stoichiometric coefficient of 1, whatever the rate of consumption of that reactant or production of that product would be, is always going to be defined as the rate of reaction. And we'll see why that's useful in the next couple of weeks.
So if you don't say you have 2 and 3, do you use the lowest?
Nope. It's always calculate what it would be if you had a stoichiometric coefficient of 1.
Oh yeah, so if you use the lowest of the 2 or 3 to get
The ratio is always going to be the same, so it doesn't matter. So that's the great thing about having a balanced equation, is that a third of a stoichiometric coefficient of 3 is the same as a half of a stoichiometric coefficient of 2, is the same as a fifth of a stoichiometric coefficient of 5. That all those rates are related to each other through the stoichiometric coefficients.
So if you have one with multiple numbers, you have to do the math for all of them.
Math for any of them will work. All right, so let's look at another example. So we have, if our world was amazing, we would run all of our cars off of this reaction. Burn hydrogen gas with oxygen. The only byproduct is water.
Is that what an HHO system does?
HHO?
Yeah, it's like electrical currents on different sheets of metal with potassium, I think, is a catalyst, and it splits the water. And
So we can pump energy in and go backwards, and then we can use that and burn it.
to your intake, so you burn more hydrogen. I had a few people I worked with, they had it in their cars, but you had the potential to blow it up.
Yeah, you can definitely blow up your car.
But they increased their gas mileage by 30%.
But it probably takes a lot of energy to do that. So, yeah, fair enough. All right, so if we're talking about the rate of reaction, the rate of the reaction can be described by any one of these. So I want you guys to click in. What is the rate of reaction when oxygen is decreasing at 0.23 moles or molarity per second? So I guess my question wasn't quite clear. The question is on the screen. What rate is concentration of water increasing when you have that rate of consumption of O2? What is the rate? What is the rate of water being produced? About 42.
Where is that? Do units matter in this one? It's not.
I'm not asking for units. All right. So we are right at the end of our time. How would we figure out the rate of production of water compared to O2? How would we figure it out, Megan? So we know that as oxygen is being consumed, water is being produced twice for every 1 oxygen being consumed. So that would be, I don't know why it has that. It's bizarre. So to get to Shane's question, this is the kind of question where you need to be able to calculate the rate of the reaction. So specifically, if we have this rate of consumption of 1, what is the rate of the reaction? And if you guys want to, if you have questions about this, you can stay after class and I'll help you with this. Otherwise, just finish the rest of the worksheet. I think that this question, a couple questions on there, and that's it.